Hello everyone, my name is Tuli. I am a performance engineer at Salesforce, just like Jonathan mentioned. And today I'd like to talk about anomaly detection at scale. I am going to try and wrap this talk up as fast as I can, so there is time at the end for questions. So as a performance engineer, I do get called on from time to time to look at our production systems and to help identify and resolve performance bottlenecks. Now, this may resonate with some of you here when I say that my biggest challenge has always been the data correlation part, right? So if I am looking at a particular performance metric for a server or a pod, as it is called in Salesforce lingo, how do I really make sure that I'm looking at anomalous behavior and that is not just the regular profile of that server or pod for that given day of the week, day of the month, or the season, and so on? So let me elaborate a little bit on that by taking a look at a couple of examples. So this is the CPU usage chart for one of our pods. And let's just assume that we found a really critical performance issue. And we identified that, we tried to resolve it, and then we introduced some new code into the system Wednesday night. Now, when I look at the CPU usage for Wednesday versus Thursday, I do see a marked difference. There is a decrease in CPU usage, but now how do I verify that this decrease in CPU is actually because of the code that was introduced into the system and not just a normal Thursday profile for that server? Now, one of the easiest ways for me to identify that and verify that is by looking at the load profile for that pod. The load profile is nothing but the incoming transactions that are being processed on this server. And now if I look at the Wednesday-Thursday load profile, it does seem similar. So now I can actually go back to my CPU usage chart and really confirm that, yes, you know what, the code that was introduced into the system really made it efficient. Now I can calculate the delta and the percentage improvement, and all is good. A simple, easy process, two-step process, basically, and very easy to do for, say, 5 servers or even 10 servers. But you all know that our production systems are made up of hundreds and thousands of these servers. So not a very scalable solution. Let's take a look at another example. Once again, this is CPU usage data for one of our pods in production. A lot of spikes here, a lot of variation here, so just bear with me for a few minutes. We're just going to visually look at this data, and I am looking at the Tuesday, Wednesday, Thursday data for the current week on this pod, right? And I just feel that, you know what, I feel that the CPU has increased. How do I verify that? I am actually going to look at Tuesday, Wednesday, Thursday data for the previous week. And yes, I do see some sort of increase in CPU usage. Once again, how do I verify that this is anomalous behavior and not just some change that happened on the server this week versus the last week? And for that, I'm going to look at the load profile for the 2 weeks. Like I said, lots of variations here, and we're just eyeballing the data, so we're just going to say the load profile does look very similar. That means it's the same transaction rates, the same number of transactions that are being processed the 2 weeks. So why has my CPU increased? And at this point of time, I could actually end up with tens of different metrics that could potentially impact my CPU usage, right? And now that I have all of these time series charts, it basically means that I have to go back and forth for each one of these metrics, look at the week-over-week numbers, compare that to my CPU usage, and then try and find the performance bottleneck. Like which metric or what bottleneck in my system is really causing my CPU to increase. Not very difficult to do, once again, for maybe a few servers, but very soon we'll realize it's not a scalable solution. So we want to automate this part of the anomaly detection process. So before I actually go into the main anomaly detection solution, I do want to give you an overview of the release and development lifecycle at Salesforce. It's a standard development lifecycle that I think 99% of organizations follow. But it'll actually give you an idea of some of the assumptions that we've made when we came up with the solution, like what is my training data, what's my test data, and so on. So at Salesforce, we have 3 major releases a year. And even though we just have 3 releases a year, changes get introduced into the system pretty much on a daily basis because of daily releases that go in or emergency releases that go in that are trying to fix either a broken functionality or any kind of performance degradation that was noticed. So we want to, like whatever solution that we come up with for anomaly detection, we want it to be able to run on a daily basis. And if possible, we want it to run real time. Because any time a change in the system introduces a degradation, we really want to know as fast as possible so that it can be resolved and any kind of customer impact can be shortened. The other thing that we want to do is, with every release that gets introduced, we want the performance profile for the release to not vary vastly from the previous release, right? So we don't want to change SLAs, we don't want to change our contracts with customers. They expect the same behavior from the system, even though we've introduced a new release. We've got new features that are being introduced, we've got new functionalities, doesn't matter. We want the performance profile to remain the same. So keeping that in mind, the proposed solution that we come up with needs to satisfy these 2 conditions. It has to run daily, if possible, run real time, and then it should be able to compare performance release over release. And if you recall the 2 examples that I talked about in the beginning, my 2 biggest challenges were the manual data correlation that I was trying to do, and then every time I was trying to really figure out and verify if I was seeing anomalous behavior, I was looking at the load profile for the server. So keeping the conditions and challenges in mind, what we did was we went ahead and listed out the metrics that we will use in our anomaly detection system. Now, to simplify things to the very basic, what I've done is I am actually measuring server health, or pod health in our case, by looking at CPU usage. Right? So CPU usage is actually telling me the health of the server. These are pretty much the metrics, the critical metrics that impact server health or CPU usage. So these metrics were not chosen randomly. What we did was went back and looked at our production historical data, looked at all the incidents that occurred in the last year, tried to figure out where CPU degraded, and then how did we figure out what metric was an indicator telling me that CPU was degrading on the system. And that is what we came up with. The load profile of the incoming transactions, very important. Anything and everything that happens on the server is actually triggered by incoming transactions, so we definitely want to keep track of that. We've got a couple of garbage collection metrics here that are actually indicators of my JVM health. So all of our systems are Java-based systems, so for us, an important metric to look at. We've got a couple of log metrics here, because log metrics are an indicator of the I/O operations that are happening on the pod and thereby directly impact CPU usage. And then we've also got a few different types of error messages here. Now, errors are an indicator of not just broken functionality, but at times will also give you an idea of performance bottlenecks in the system. So we want to keep track of these 8 metrics. All right, so the first thing that we did was we wanted to find out if there was any kind of relationship between these 8 metrics and the incoming transactions on the pod. And this is what we came up with. Now, this is just raw data dump. And here, the x-axis is basically the incoming transactions, and the y-axis are the individual metrics that we're trying to measure. So we're trying to find a relationship between the incoming transactions and these individual metrics. And like I said, this is just raw data dump. We haven't cleaned up the data or anything. So there are a couple of exceptions here. But if you looked closely, there does seem to be some kind of relationship. And that relationship seems to be linear. So what that means is that we can actually use linear regression techniques to base our anomaly detection system on. Right? So this is the well-known linear regression equation. Don't think I need to explain this in a lot of detail, but for us, the independent variable xi is basically the incoming transactions. The dependent variable yi is the individual metric that I'm trying to assess with respect to the incoming transactions. The regression parameters will be found from the data, and then the error, or the residual component, is something I'll talk about in just a couple of minutes. All right, so now we're actually going to talk about the solution itself. It's a really simple 3-step process where the first step is to find the distribution for the normal, right? So the data that is here on this slide is basically just CPU utilization versus the incoming transactions to my pod. And the goal of linear regression is to fit this data with a line such that my error value is minimal. Right, so I am actually going to run my linear regression code. This is the output for it. This is where I actually get my regression parameters from. And the R-squared value, at least for this data set, was 0.97, which basically means that at least 97% of the data, the regression line fits at least 97% of the data, which is good enough. So we've got our linear regression model. The next step is to find the error, right? The error value. So how do we define a residual or the error value? It's nothing but the difference between the actual value and the predicted value. So if I wanted to visualize this definition for this data, once again, this data is for transactions and CPU usage. It basically means that I am actually going to go ahead and fit this data with my linear regression line. I pick up a data point, say that's my ith observation here, and I calculate the distance between that point and the fit, and that is actually my error value, right? Now, what is missing from all of this is any sense of distribution of these residuals, right? So to elaborate on that, if I got, like, for example, the error value here was 5, for example. Is 5 more or is 5 less? And then remember, we have 8 different metrics that we are trying to use in order to detect anomalies. How does an error value of 5 for one metric compared to an error value of 5 for another metric, right? So to address this dilemma, what we're going to do is, instead of using raw residual values, we're actually going to use z-score values. So a z-score is nothing but a standardizing value that actually measures the distance of the data from its mean in terms of standard deviations, right? So since this is a standardizing value, we'll actually be able to say how much better or worse is the data from its mean in terms of standard deviations. And now this definition can actually be used for all the metrics that we are measuring. So that's what we're going to do. The third and the last step of the solution is basically trying to set a threshold. How do I know that my data is anomalous or not? And to use that, to set that threshold, we will actually use the 68, 95, 99.7 rule. It'll be easier to explain this in terms of an hypothesis test. So if I took this as a hypothesis test, and I said my null hypothesis was that a data point is not an outlier, then if I actually got a really small p-value, I will be able to reject that null hypothesis, right? So to give you a couple of examples. For example, if I had a z-score value of 1, and I had a p-value of, say, 0.32, it basically means that my algorithm is going to categorize the data point as an outlier incorrectly 32% of the time. But the corollary is also true, that 68% of the time, the data point will not be considered an outlier, right? If I had a z-score value of 2 and I had a p-value of 0.05, that means that 5% of the time, a data point will be considered incorrectly, will be considered an outlier, but 95% of the time, it will not be considered an outlier. So when we're trying to set a threshold, there is always a trade-off between certainty and coverage. And at this point of time, when we're just starting off with our solution, what we really want from our algorithm is as many data points, as many signals that we can get. So for all the examples that I'll be talking about next, we've actually chosen our threshold to be a z-score value of 1. So anytime I get a data point whose z-score value is 1 or greater, we're going to categorize that as an outlier, otherwise not. All right, so we've seen those 3 steps. Now let's put all of that together and see the algorithm in action. Right, so this is the output of the anomaly detection solution. And the layout is actually very similar to the one that we started off with, where we were trying to figure out if there was any kind of relationship between metrics and the incoming traffic. So remember the 2 conditions that the solution had to satisfy. It had to run daily, right? So the blue and the red dots that you see here, they're actually daily data. The data is being collected every 10 minutes. And the really big circles that you see, the big green and red circles, that is actually the output of the algorithm at the time of the measurement. So that's the current time at which the algorithm was run. So we've tried to make, it's not really real time because it's not running every second. It is running every 10 minutes, but kind of real time for us. The second condition that the solution had to satisfy was that it had to compare performance release over release. So what we've done is we've taken the previous release's data as the training data, and the black line that you see, the black diagonal lines on these charts, that is my linear regression fit line for the previous release. And all the current dots that you see, the blue and the red ones, are my test data, which is the current release. So it is actually satisfying both the conditions that I started off with and the 2 challenges that I had, right? So every time when I was verifying behavior, I was looking at incoming profile. That information is already included in these charts because the x-axis is the incoming transactions. So I don't have to go back and forth looking at time series charts for like what happened last week, what happened the previous month, what happened previous release. All of that information is right here. So all that manual data correlation is actually automated. All of that information is included in this very chart. The colors are actually, blue means that it's not an anomaly. Red means that an anomaly was actually detected. So now, as a performance engineer, if I actually saw something like this for a pod, and I'm seeing like my GC times have actually gone up, but my GC counts are actually down, and I know from this chart that it is really anomalous behavior, I can now actually go back to the code and I try to identify why that is happening, try to resolve that issue so that if there is any kind of customer impact, I can shorten that. Similarly here, at least in this example, there are a couple of errors that have actually gone up, right? So once again, I don't have to waste time going back and forth trying to figure out if this is really anomalous behavior or not. I know it is, and I need to fix this as fast as I can. We can extend this same solution to more granular level metrics. For example, in this chart, we're actually looking at the different types of transactions that my pod is processing. So the first column here is the count, so the number of times that particular transaction type was processed. The second column is the average processing time, and then the third column is the cumulative processing time. And the horizontal lines that you see, the horizontal, the pink, the yellow, and the blue lines, they are actually the median, 25th, and the 75th percentile values for these metrics for the previous release. So once again, we're comparing release over release. And for example, this very first row, I can see that this particular transaction type is now being processed more in this current release versus the last release, right? So the cumulative times are up, but currently when I took the measurement, you see the big green circle. It seems to have gone down, but something that I need to keep an eye on, because now these transactions are being processed more. The interesting observation here is actually this last row, where you do not see any of those horizontal lines. So what does that really mean? It means that this is a brand new transaction type that was introduced in this release and did not even occur, like it was not even present in the previous release, right? So we've all got these huge distributed systems. Like I said, changes come in every day. Releases bring in major changes. And as a performance engineer, it's very hard to keep track of every change that gets introduced in a major release. But this is actually a good way to keep track of that, right? So I know that this is either a brand new feature or some feature that was enabled in this particular release, but something to keep track of and know about it. We can actually go one level deeper, and for a particular transaction type, I can now look at some performance metrics for that transaction type, right? So for the transaction type that I'm looking here, I know instantly that my DB get connection times have actually gone up. Once again, this is release over release comparison. This is daily, almost real-time evaluation of the metric. So I know that this is anomalous behavior. I should actually go back and try and figure out why these connection times have gone up, try to resolve that so that I can actually lessen any kind of either pod performance behavior impact or customer impact. All right. So what we've done so far is we've talked about this really simple anomaly detection solution. And we've also seen how I can extend the solution to the different metrics that I'm measuring. What we haven't talked about is how do I scale the solution out in terms of the number of pods and servers that we have in production. And for that, this is the table that we've come up with. Now, the table is actually trying to rank or prioritize servers based on how unhealthy they are. So there are two approaches that have been combined here. And the benefits of something like this, a summary table like this, is, for example, you've got these thousands of servers in production, and you've got 20 of these servers that are all blinking red. Which server should you look at first, right? And that is what this table is trying to answer. So the first approach is basically just to count all the number of outliers that are found, right? So this is talking about server health. So we're measuring server health based on those 8 metrics that I talked about earlier. So out of those 8 metrics, like how many of them at the time that I'm evaluating this, how many anomalies were detected? That's column number 3 here, which is the outliers. The second approach is to calculate the z-score value. So what I'm doing here is to get column number 4, I'm averaging out all the non-negative z-score values. So remember, my threshold to identify an outlier was the z-score value of 1. So all negative z-score values basically mean that there was some kind of improvement that happened in terms of that metric. But anything higher, from 1 and higher, basically means that it was an outlier. So if I went ahead and added and averaged out all z-score values, a server would actually appear more healthy than it really is. So we're just picking out the non-negative z-score values. And that is column number 4 here. And because of combining these two approaches, you may end up with a pod with more anomalies ranked lower than a pod with fewer anomalies. And that is all because of the z-score value, which is telling you about the magnitude of the severity, right? So that is how we could scale this out to the servers in our production systems. So now what I want to do is I just want to take a couple of minutes and talk about another technique that has proved really beneficial to us when we've tried to scale out anomaly detection solutions, and that is clustering, right? So you may have noticed that in your systems. It is definitely the case for us, where even though we have the same release getting deployed on all our production servers, so the same piece of code running on the servers, the servers behave differently. And there could be a multitude of reasons for that, right? So it could be the kind of customer that is running on the server is different. It could be because of the hardware. The server hardware is different. It could be because of the number of servers that make up my app tier. It could be because of the workload profile is different. So whatever the reason, these servers all behave differently. And what we want to do is we want to apply our clustering and classification algorithms and group these servers into little clusters. So the benefit of doing that is that now, instead of keeping an eye on and monitoring 100 servers, now I can actually just pick out a representative server from these clusters. So for example, like in this case, I've got 5 clusters. All I need to do is look at those 5 representative servers from these clusters. And anytime I notice a kind of performance bottleneck or any kind of change in the system that could lead to a degradation in performance, I will know exactly which other servers will be impacted the same way. And that basically will tell me what the customer experience is going to be for that cluster. If I know, like if you have this really big customer running on a pod and the representative pod from that cluster is showing a performance bottleneck, I know it actually drives the sense of urgency to like fix that problem, because you've got this really big customer sitting on that cluster and you don't want to, leave them high and dry. And get any kind of performance bottlenecks for them. So anyway, so that is what we're doing. So what we did was we applied our clustering algorithms to the different kinds of hardware that we run in our production systems. We went ahead and clustered pods based on the different workload profiles, that is, all the different types of transactions that get processed. And what we did was we looked at the peak transactions that were running on pods, how many hosts make up our app tier, and so on. We combined all of that, and we got something like this. So obviously I had to blurry out the names of the pods here, but you get the idea. So we've got these 5 clusters now for our production pods, and now I just need to monitor representative pods from these clusters, and then I will be able to tell which other pods and servers will get impacted if I do find any kind of a performance issue on just one of those pods. All right, so with that, I actually come to the end of the presentation, and we're happy to answer questions if there are any.